All right. So I think we'll probably get through this topic today. This is complicated and this is hard. As you know, this is the second time I've taught this class. And the first time I taught this class, I really fumbled on auxiliary particle filters. I gave a lecture on it and I screwed it up. No one understood it. I don't think I understood it well enough to be lecturing on it. And then I came back and gave a second lecture. I think it went much better the second time. So this is at least clear in my mind, and I'll do what I can to explain it to you as well as I can. There's a lot of math today that I am going to go through with you to explain where the equations come from, because in the references I've been able to find, as you know, if I don't explain something, if I can't understand something that is written by others, and I go through and try to derive the math on my own and figure out where the equations came from, and if I do that well, then I think that's helpful to students, and so I put it on the slides so that we can go through it that way as well as using the references. Here's an outline. The big idea behind auxiliary particle filters is to use the measurements in a different way. Let me do a quick review. We've talked about basically two particle filtering algorithms so far. In one, the particle filters, the particles we propagate forward according to the process model. So we just say, forget about the measurements, move them ahead in time, just as though you were following the process model and not taking account of any of the measurements. The second important instance here, the second technique that we used, instead said, move the particles ahead, taking into account your measurements. Use a linear model, in which case we can approximate, given the measurement, where the particles ought to go on average, and put them within that narrower range. So it was taking account of the measurements. And that was different. That kept them tighter, it kept them more consistent with the measurements, and that meant we had to resample less frequently.
Did that have a name?
It did. The problem is, I don't remember what the name of it is. I could switch to it, but I'm blanking on the name. Do you have it written down, Reed?
Just have optimal importance densities and local linearization, but I don't know if that would be the name.
Thank you. That was it. It was optimal, and an optimal in quotation marks, air quotes for those of you that are listening, optimal importance density estimation that was based on an approximate linearized model. So we approximated the dynamics as linear, and in the case of linear, it becomes optimal, defined by that weird optimality criterion that I had discussed in the last couple of lectures. So we had the approximate optimal, I'll call it that for short, approximate optimal, and then we had the simple, where we're just using the prior as our importance density. And this is a different approach. This is the big idea behind this, and it'll take some math to explain it, but the big idea behind this is that rather than taking our trajectories and then pushing the particles forward in time, as the two previous techniques do, instead there's a sampling step where you pick the best trajectories. You're essentially picking the parents before you let them propagate forward in time. That's what auxiliary particle filters in its simplest sense is about. And let's just go through it. So we know from our earlier discussions that what we're trying to estimate is either the marginal posterior or the joint posterior. And as we also talked about in sort of the opening remarks, is that our approximation is based on this very nicely written sum of delta functions that are located at the trajectories. And this is in a very high dimensional space, as we've talked about, that grows with time. And the weights are normalized to be 1. And this estimate is completely defined and parameterized by knowing what the particle trajectories are and knowing what the weights are that are associated with them. So this is just a review of some of the ideas of... And the weights, as we know, are the ratio of the posterior divided by the importance density. And what we really want, in order to make maximum use of all of our particles and have a really good estimate, is we want all the weights to be constant. We want them all to have the same value. That's the best case. Otherwise, we're not making good use of a lot of computation, and a lot of the particles end up not contributing to our estimates. And so that's important. And the best way to get that ratio to be constant is to have Q equal to P. What we'd really like to do is draw samples from the posterior itself, but we didn't have a good way of doing that. I guess I've got all these points down here. So it seems like this is hopeless. And I said this was hopeless, and I used that as the basis for the various choices we made for picking other importance densities, is the idea that we can't draw samples directly from the posterior. I'm going to call that back into question in this lecture and take a closer. So we know by Bayes' theorem, which we've used many times now, that we can factor a joint as a product of a marginal and of a conditional and a marginal probability. And if we go through and we factor this in the way that we've done it a few different times, we end up with essentially the basis of the optimal equations that we used, where we've got the joint is proportional to the likelihood times the prior times what the joint was at the previous time sample. So we've used this a number of times. We used this in our calculation of the weights, and we used this when we were doing the optimal tracking in a single dimension. So that is, it should be something we've used a number of times. And this is just a repeat of that same equation at the top of this slide. And then let's take a closer look at some of the other things we did earlier and maybe consider undoing some of those or picking a different path. Another way to factor the joint posterior is to write it as the product of x of n conditioned on the past values of x of n and y of n, and then multiply that by the past state. So this is the past state conditioned on all the measurements up through the current time. This is a different way of factoring than what we did before. I've got the other equation up here. This is one way to go through and factor that. This is a different way. And we actually did this before when we were looking at the importance density, and we were talking about how we might factor it. But note that this is not equal to this same thing conditioned on y of 0 to n minus 1. The measurement at time n has an effect on what the joint is. And when we were designing or selecting our importance density that we were actually going to draw particles from, we wanted it to be a nice recursive equation. So if we compare it to the top equation for factoring the joint the way we did, this is conditioned on the past values, and so we chose our importance density to also have it conditioned where we could factor it as what it is at time n conditioned on the past multiplied times this term, which is the past trajectory conditioned on the past measurements. We didn't let the past trajectory depend on the current measurement, and that was a design choice. So that when we take the ratio of P over Q, we end up with this nice recursion for the weights, and it saves a lot of computation that way. But it was by choice. And I tried to emphasize that when we were going through it, and there's nicely in this lecture, it comes back again as being important. So what I'm going to call into question, or what I want us to reconsider, is whether we can actually draw particles from something that's closer to this. Draw particle, and think of particles as being complete trajectories. So imagine drawing trajectories instead of advancing them one step at a time. Imagine now recreating the entire trajectory possibly at each time sample. And yes, we can move this one ahead this way, but when we're considering the trajectory from time 0 to time n minus 1, that we're taking into account the most recent measurement. And that's a different idea. That was something that we said, no, it's too complicated. We don't lose that much by doing this. We end up with a nice recursion for the weights. So let's just pick Q this way. It's hard enough to pick Q as it is. Why make it any harder? And there's an advantage to doing it this way. And with this approach, with auxiliary particle filters, we're going to go back and say, no, let's take a closer look at that and see if there's a way in which we can get something closer to the optimal importance density. I think I made all of these points in the earlier slide. And again, the thing I'm calling into question, and I know there's maybe a number of you that are going to be watching this online, so I'll try to use my pointer here on the screen. So the thing I'm calling into question is whether there is a way to draw the past trajectories from the using all of the measurements. So using all the measurements from 0 to time n. So we don't just propagate them forward and then we're done. We're going to re-examine whether we did a good job picking those past trajectories based on the current measurement. It's okay in principle? All right. So if we're going to do optimal importance sampling, what we really want to do is make both of these equivalent to their posterior values. In other words, we would like this Q to be approximately the same as what the P would be there. The posterior would be there rather than importance density. And likewise for this. We want to make both of those essentially as close as we can. And, you know, at first glance, this seems like an impossible problem. Because what we're talking about is drawing samples from a distribution of entire trajectories that go from time 0 to time n-1. You know, remember with Q, we're generating particles, but now we're talking about entire particle trajectories rather than just advancing the particles one step forward at a time. And so in this case, I'm asking the question, okay, we get a new measurement at time n, and now we want to draw new trajectories. And so if you've got 500,000 samples, the idea, and 10,000 particles, the idea of generating entire past trajectories from scratch from a new importance density would seem computationally infeasible. But it turns out there is a trick. There's a way around that. We don't have to go through and regenerate all of the trajectories. And instead, you sample from the ones you've already generated. So what would appear to be sort of a misstep and headed in the wrong direction, we're going to make things much worse. So the idea is, in part, that we already know what the posterior is approximately based on the representation we have of the joint posterior. We've seen this equation a number of times, and it simply says, okay, we've got a representation of what the past is, and is there a way that we can leverage this approximation to draw samples from the thing we're interested in? That note that this goes up to time n instead of time n-1. So what I've highlighted in red there is a difference between these two equations. So this alone isn't good enough. We need more. And here is where the trick comes in. In order to relate this one way of relating the past trajectory, the past posterior conditioned on measurements up through the current time, is to use this integral, essentially integrate out the state at time xn. So if you do this, you end up with a type of a marginal distribution because we're integrating out x of n. And this joint is something that we've broken up a number of times before, and we've seen before. This joint, and we've been through these equations many times. This is just the standard way that we factor the joint. I probably didn't need to write it out again. Likelihood times the prior times what the joint was at the previous time sample. So if we take this expression, if we take this expression for the joint and substitute it into this integral, then we get this. The thing that we're interested in drawing samples from is proportional to this long integral. And if you look at that, the previous joint, this term here, is not a function of the variable of integration, and so we can factor it out of the integral and write it this way. So I know this is a lot of math, but bear with me. This will bear fruit in just a minute or two. Now, the second thing we can do is that we've got an approximation of what the joint posterior was at time n minus 1, which again is the sum of delta functions, where it's at time n minus 1, but it's still just a sum of delta functions. And so if we substitute that in as an approximation, then we end up with an approximate value for the thing that we want to draw samples from. So again, we want to draw samples from this, of the prior trajectories, and we substitute in the approximation we have up here, then we end up with this expression times that integral. Being a little bit sloppy with the math, but we'll ignore it. The sum times the integral is equal to the sum of each term times the integral. And if we combine the integral with the weight, we can write this as this factor v of n minus 1. And I apologize, I forgot and didn't look up what these are called, so I'm just going to call them the parent weights for the sake of today's lecture. So we end up with these parent weights times this distribution. And notice that we do have the measurement in here. The measurement is affecting what that parent weight is. That's where it comes into it. Oh, I do call them the parent weights. That's convenient. So, so this is the same as on the previous slide. In here I've written out explicitly what that parent weight is. So it's got this integral, and we'll deal with the fact that it's got a multi-dimensional integral in it a little bit later. But for now, at least in principle, we've got a distribution that is approximately the same as the joint posterior. And that's useful to us, well, I'll explain in a minute, because we can draw samples from it. So if we combine that with our earlier result, then our importance density for the entire trajectory is equal to the product of this term that we had before here times that same thing, the sum of impulses. But now these weights really represent how probable that trajectory is, taking into account the measurement at time n, even though it's the past trajectory. So it's different than what we've been. In order to calculate the weights, we're going to need a representation that we can use in that ratio. To calculate the weights, it's, there's a P over Q factor, and we need to know what each importance density term is. And so we've got this as our importance density, and it's multiplied by these weights. But it also depends on the weights, and with a little bit of math, we can actually simplify this. So if we're looking at the importance density evaluated for the jth particle, we know that it's given by this expression, and we just substituted in essentially the jth particle here, where that was a variable before. So rather than the density evaluated at any trajectory point, this is evaluated at where the jth particle is. If we multiply and divide by the weight, and we get that, and if we look at the various terms, this ratio, all of the terms in the sum are 0, except for when j is equal to I. There's only one term in that sum that is non-zero, because these are both evaluated at the trajectories. And so if j is equal to I, if that's only only term of that sum that's non-zero, then we can index this by j just as well as we can index it by I. And that means it's really a constant, and we can bring it outside of the sum. And when we do that, we end up with this ratio, the parent weight divided by the trajectory weight at time n minus 1, multiplied by this sum. And that sum is our approximately the joint posterior evaluated at time n minus 1 for the jth trajectory. So again, I know there's a lot of math there, but what we gained in going through these equations is going from this generic equation at the top to something that we can relate to what the joint is. And I should probably have a hat on top of that, because that's our approximation of what the joint posterior is. So in order to use this, if we want to calculate the weight, we know the weight is equal to the ratio of the posterior divided by the importance density. We're using a different importance density today than we have been. So the P is the same as before. The Q is different because now we've got this depending on the measurement at time in. And if we substitute in the result from the previous slide, then we get this is equal to the importance density that advances us from time I to time, from time n minus 1 to time n, times this ratio of the parent weight divided by the particle weight times our approximation of that joint posterior, the previous time sample. And so then if we substitute this into our expression for the weight, and you go through and you do the math, you end up with this nice factoring. And this ends up, if we accept that these two are approximately equal, remember this was our approximation of the joint posterior, not what it really was. But if we let that ratio be 1, then approximately this is equal, the weight at time n is equal to what it was divided by the parent weight times a ratio that should be familiar, that we've seen before. The likelihood times the prior divided by the importance density that represents how we move the particles forward one time sample at from time n minus 1 until time n. I will bring all those together. So far I haven't stated what that portion of the importance density is, of how we draw samples from time n minus 1 and move them forward to time n, how we move our particles forward in time. You can use anything you want, including the approximate optimal importance density that we talked about last Wednesday. But for the sake of these slides and to get a simple result in a complicated topic, let's say that we just use the prior for now. So we just move the particles forward the same way that we did the first time we talked about particle filters. So we substitute that in, and we get a similar cancellation that we've seen before, where the prior in the denominator cancels the prior in the numerator, and we end up with a very simple expression for the weight updates. The weights at time n now are just equal to what they were times the likelihood and divided by whatever the parent weights are. Is that okay? Let me pause for a minute. Do you guys have, I know this is complicated, but do you guys have questions so far?
Is that the W and sub I?
It is, thank you. And I should also have said X and I as well.
So wait, in this step we're going back to using the prior as our importance distribution?
Well, what probably isn't clear so far, and I'll talk about it in a minute, the way in which this is different. We move the particles forward in the same way as what we talked about last week, except before we move them ahead, we're going to pick parent trajectories. And that selection of parent trajectories is new. That's something we haven't done previously. So what's new in this is the denominator, the fact that we've got a parent weight. That's new.
That's not going to save us from degeneracy problems, is it? Or is that not the goal here? Even though we're weighting the weights, we're still drawing the particles in the same way. So
it seems like they would go in unlikely places.
Yeah.
But if they go in unlikely places, then the parent weights get really small, and we don't tend to sample those. They're sampled with a lower probability. And so pre-selecting the parents handles the degeneracy problem.
Okay.
Whereas one way of handling it, more about that when we get towards the end. So here's what we ended up with. We've got a very simple weight update equation for the weights. We're moving our particles forward in the same way that we were previously. The only difference is that we're selecting parents before we let them move ahead. So I was trying to think, what would the analogous political or demographic policy be around this, and you end up with some sort of this would be different than killing off offspring, but it's almost like the China policy in some respects, where it's like you only allow some parents to propagate and not others. So it's not quite the same, but it's kind of there's some analogous idea when you talk about parents and children. I'm not sure what it was. But in any case, the idea is that we are randomly selecting the parents that can move more particles forward and how many they can move forward. And it's based on this weight. So not all parents are going to have children, but all children will have parents under this scheme.
It's kind of reminiscent of some, evolutionary algorithms and genetic algorithms where generate every generation. If you want to speed up things to converge somewhere, you sometimes decide to bias towards the best parents, which the algorithm does by itself, but you can tweak things like that. So it really reminds me of that.
That's a good point. I'm sure people have thought more carefully about the overlaps and the differences between particle filters and genetic algorithms. There are some analogous ideas. Yeah, it's true. So the
Are we duplicating parent particles, so we're not experiencing?
We're selecting parent trajectories with replacement.
Okay.
So the way I've been thinking about it, and I guess the way I've been thinking about it probably isn't appropriate because I'm too hung up on what the analogy would be if it were a governmental policy. So it's not really true that that some parents get to have multiple children and some parents get to have no children. It's more like you're picking the parents and you're replicating some of them. So some of the parent trajectories are the same. There's sort of a copied heritage for the particles as you move forward in time, but it's not exactly that they're the same. The way you represent it in memory is that they're different usually. So you've got copies of the parent trajectories. And the way that we go about them, if we know what the weights are, we can do this exactly the same way we do resampling. It's just rather than resampling based on the particle weights, we are pre-sampling based on the parent weights. But it's the same algorithm that we talked about before, and you can do it efficiently. It breaks parallel computing approaches, but it's the same idea otherwise. And again, really, the important thing is not whether we're killing off the parents or what's happening to them, or whether they're allowed to have children. What really matters is that we are using the measurements to help us make decisions about the particles. And in this case, rather than using the measurements to figure out how to sort of steer the children from the particles we have, which is what we used last week, instead the idea is to select parents that are more consistent with the measurement that we've got at time in. So it's a different approach with more or less the same goal of getting an importance density that is closer to your posterior density. So that's the idea, the big idea. And I've read the original article by the authors that came up with this. They called it the dependence adaptation, and I thought their paper was hard to follow, but full. So we're using pre-sampling with auxiliary particle filters. And one of the things we needed that I sort of flew by earlier as we were getting to this point is the parent weights. The parent weights had a problem associated with them. We've chosen, just to recap, our importance density is equal to the product of the thing we use to figure out how the parents are going to create their children, which in this case we're just using the prior in this set of slides. You don't have to. You could use that optimal importance density that we talked about last week if you wanted to. You can plug that in right here and merge it with auxiliary particle filters and end up with something even better, arguably. But for this set of slides, I just used the prior. So that turned into the prior. And this thing that we thought was going to be so troubling ends up just being a sum of impulse functions weighted by these parent weights, where the parent weights are given by this expression. And if you were to try to code this in based on what we've talked about so far, where you would hit a wall, I think, is when you hit this integral. I say, okay, great, I need the parent weights so that I can pre-sample. And you look at the equation and you say, oh shoot, the parent weights are equal to the particle weights at the previous time step multiplied by this integral. And that integral isn't something that we can evaluate efficiently and easily. And so what do? And a common choice is to just throw in another approximation and cross your fingers and hope. And the approximation that's used often is to assume that you don't have any process noise. If you don't have any process noise, then this integral, the prior here, ends up just being an impulse function. The located at your process model before you add the noise is a function of what your state was at time n-1. So this is what we use to advance the state. And then usually we add noise, but this is ignoring that noise. And by ignoring that noise and being an impulse function, that integral now becomes something that we can evaluate analytically and becomes very simple. In fact, that integral, when we substitute in this model and assume a state dynamics or deterministic process model, so our process model that this is based on looks like this. We end up with this impulse function. You substitute that into the integral, and you end up with your parent weight being equal to your previous particle weight times the likelihood evaluated at this value. So you know what your parent trajectory is up until time n-1, so you substitute that in, put that into your process model, which advances it in time one step, and this then becomes the likelihood function. And so that's what is often used. There's other things you can do. There are, it's been argued that maybe rather than just locating it there, you should use a mean or the mode or the median or draw a random sample. I mean, there's a number of different ways that you can take your process model and generate a model forward to approximate what that integral is. But this is a common choice, and it's simple, and in practice it works pretty good. So there are a number of approximations that this technique is based on, but we're working with, I think, a very difficult problem in general. So if we use that approximation that I described earlier that we just went through, then our weight update equation is still this, but we can get a further simplification because now we said this is going to be equal to what the weight was times this. And then something sort of magical happens. I really like this result. If we substitute that in, this expression in, for our parent weight into the expression we had, this is what we get for the numerator and this is what we have for the denominator. And you get a cancellation of these weights. And so the particle weights at time n now are just equal to the ratio of the likelihood function divided by this that's very close to the likelihood function. The likelihood function evaluated at by advancing your particle from time n-1 one step forward, where this should be with an I superscript here. This is also for the ith particle, but they look very close to one another. And if we had a deterministic process model, then this would be 1 and the weights wouldn't change, which is a nice result. I mean, that's what this assumption was based on, is that our process model didn't have any noise and there was a deterministic way of moving our states forward in time. Now, if that's true, you wouldn't actually need the measurements. You just need to know what the states was initially and you could propagate it forward indefinitely. But setting that aside, it's nice that in the deterministic case that this ratio ends up being 1, and so your weights end up being all constant, which is kind of what you would expect when you think about it enough. Another nice thing is that Reed, you'd asked about, well, don't we still have degeneracy and don't we still need to resample? But if you look at it in this case, the weights are equal to this ratio, and there isn't this recursion where the weight is equal to what it was times some ratio. And so we're not driving all of our weights rapidly to zero through this series of recursive multiplications like we were earlier. It goes away in this case because we're using the measurement at time n to pre-select the parent trajectories. So that's cool. I mean, there was a lot of math there and a number of approximations. But at the end, you end up with an algorithm that actually is pretty simple.
But it is recursive, right?
It is recursive.
Right.
Yeah. Yeah, it's still recursive. So, there's a number of alternative algorithms to the simple sequential importance sampling algorithm that we talked about earlier. Again, the key idea is using the observations to pre-select the parent trajectories before you advance them one more step in time. This technique, according to the literature, is reportedly a little bit less sensitive to outliers. And that sort of makes sense because you're using your measurements to guide where your particles go. So if you get an unusual measurement, you'll pre-select parent trajectories that are more consistent with that measurement. And so through that, using the measurements to pre-select your parent trajectories, that makes it less sensitive. But keep in mind there's a caveat, and that is that the straightforward method that we're using and that I went through assumes that we've got a deterministic process model. And that's how we got around evaluating that integral to calculate our parent weights. And so it assumes there's no process noise. If you've got a lot of process noise, then this may select the wrong parent trajectories or select parent trajectories that aren't good. It could actually have worse performance than the sequential importance sampling. So when you think about auxiliary filters, you shouldn't just think, oh, this is better than the straightforward algorithm. Instead, I would encourage you to think that this is good in some circumstances. And the general rule that I would give you, the general guide, is thinking about how much information or how deterministic your process model is. If it's really good, if there's a lot of information in the dynamics that you've modeled, then this may be a much better algorithm for tracking. If it's not, and you've got something that's closer to an estimation problem, a little bit like the homework example, Nathan, that you went through on Wednesday, then this probably isn't going to be as good. So that's the general rule, as well as I understand it, is to use this one compared to the other ones we've gone through that you've all used. So any questions on that? Do you guys want to take a break, or do you want to go through the example and break early? How's your stamina? Good?
Okay.
It's an example, so it's not as much math that we're going through. And I see, usually it takes me about an hour to get through 30 slides, but we've been going pretty fast today. So if you guys are okay, we'll continue and we'll talk about that, and then we'll get to break a little bit early. Okay, so here's the algorithm. And I updated this just before the lecture. I caught a bug where this had a superscript of I instead of I-1. So if you printed these out in advance, you probably still have that bug. So this is the simple sort of one-slide summary of the auxiliary particle filter with some specific design choices, such as is this one, about how to handle approximating that integral that enables us to calculate the parent weights. So the first step is go through and calculate your parent weights. Figure out how important the parents are. Normalize those weights so that they sum to 1, as always. And then sample the parent trajectories using those weights. And this is the same sampling algorithm that we used to do resampling earlier, in the earlier algorithms that all of you have worked with. So this is the same, it's just that it's using the parent weights to select parent trajectories rather than the particle weights to select the total trajectories. So that's the only difference. And then we go through and we draw our particles to move them one step ahead from the new parents that we've selected that were deemed worthy. And sometimes you get the same parent more than once, or I guess you also think of it as one parent may have multiple offspring, but In any case, you then move your particles all forward one time step, and then you calculate the particle weights, and then you normalize the particle weights, and you're done. And you do that recursively for each time step. So that is the auxiliary particle filter in its simplest form. And there's some variations on this, but that's the basic idea. All right, and then the example. So you guys have seen this before, and I am working on more examples, but a lot of my time goes into preparing the slides and making sure the ideas are right rather than creating new samples. But this is familiar, so you have an idea of what to expect. We've been through this a number of times. I won't go through it again. And some design choices. So I chose the simple case for the importance density to move the particles forward one step in time, and I just chose the prior. Again, you could have chosen the optimal. That was an alternative that we talked about. You could have chosen something else, but for this example, I just chose the prior. Number of particles. How do you select this? This is arguably one of the most important parameters, and in this case, I chose just 100 particles. I said to push the limits. I'm a little embarrassed by that statement now that we've seen from Reed's impressive optimization going up to 100,000 particles. But in any case, I'll leave it there at 100 particles. No, it's a pleasure as an instructor to be upstaged by a student. It's a good thing. And then for the estimator of the state, I'm just going to use the mean in this case. Even though I know it's multimodal and the mean may not be in the right location at some times, I'm still going to use that as the estimate of the state because that doesn't occur that often, and I think we all...
Measurement, your process noise in this problem.
You know, I think that was specified on the code is on the website, so we can get the process noise from that, but I don't remember off the top of my head. It should have been included in the slide, as well as the initial state.
Look at how that compares, because it's not the determining factor of this new...
Oh yeah, that would have been a good comparison. That's a good idea. Maybe I'll update these slides and we can look at a few different process noise levels and see, does it break down, especially if we were to compare it to the sort of vanilla.
We did the optimal, right? You could compare it to that.
Yeah, you could. Any of the previous two. I think we've talked about basically two particle filtering algorithms so far, and this is the third. So yeah, we could compare them. All right, so we've seen this before. This is the single run that I used to create the synthetic data. So in this case, because it's synthetic, we happen to know what the true state is. I also made a sort of late update to this slide because the way the parents were chosen, there was sort of a lot of crisscross, and I didn't unlock the history of the particles correctly. It's a bit weird. You go forward, and then some parents drop off, and you end up with some particles now that have a shared heritage. And whenever I had that, you'd see sort of a vertical line. So there were a lot of vertical lines crossing in the way that I represented this. We didn't run into before, where a trajectory would go, and then it would just end, and then you'd end up with new ones up here that could continue on. In this case, we've got the parents that are changing all the time, and so you maybe have one particle going along, and then suddenly it gets a new parent, and it comes up here, and so there were lines drawn all over the place, and so I just plotted the dots to show kind of visually what the distribution was of the particles as we move forward in time. So it's just a slightly different way of visualizing it. And you can see regions where there's multi-modes. You can't see how high it is because it's not the same as looking at a density, but it's went and where they didn't go. The question about degeneracy was a good one. And you can see this is a plot. We've seen this type of plot a number of times before, looking at the variance of the weights, which we'd like to be very small, looking at the weights themselves on both a log scale and on a linear scale. And I think especially in this middle plot on the log scale, you can see that they're not weights that are dropping off and headed towards zero for the reasons we talked about earlier. So by doing pre-sampling, we're accomplishing a lot of what we were accomplishing before with resampling, which is good. And then here we see, so you don't have to set a threshold. I guess that's another nice thing about this algorithm. There were some design choices that we had to make, but in the earlier algorithms, you had to specify a threshold for the number of effective particles that would trigger resampling. And with this, you don't, because you're basically pre-sampling at every time step. And so there's no knob that you have to turn and justify when your instructor asks you about why you chose that. So this shows the marginal, this is the particle estimate of the posterior. And there is yellow, as we had with Nathan's. It's really hard to see on this projector because the projector's dying, but there is a nice 95% confidence interval, and it's doing well. Here is with the optimal numerically computed posterior. And if you compare those two, and I'm going to have to stop recording for just a bit. It's only with 100 particles too. I mean, obviously with more it would be even better. I guess I'll spin that so it's a positive. And you can see that the green is also pretty much right on top of the blue, which is where the true mean is, calculated by the numerical techniques. So it's working well without resampling, and that's good. You know, it's a bit of an improvement from what we had before. What I haven't done is show a comparison of the computation involved, and I haven't done that in part because it's such a dicey thing to do. It depends on how skilled you are at optimizing and profiling the code. But clearly going through and doing the pre-sampling is roughly analogous to doing resampling. And so this will be more computationally intensive a little bit compared to the simpler algorithm. So it's a little bit unfair to say, oh, it's more accurate, you don't have to set a threshold, because really it's just like setting the threshold such that you resample at every time step. It's not that different in that respect, computationally. So that's more or less it. That's auxiliary particle filters. You guys have any questions? Okay. Well, for homework 5, that's going to be due next week, a week from Wednesday. I'm going to ask you to implement either the approximate optimal, it sounds like an oxymoron, the approximate optimal, or the auxiliary particle filters that you've seen here, or the something called the Viterbi particle filters that aren't very popular but are really cool and really neat, and we'll probably talk about those, well, actually probably next Monday, so you may not have enough time to implement that for that homework assignment. We'll see how things go. And I look forward to your homework presentations on Wednesday. Okay, good. We'll stop there. We're stopping quite a bit early. I hope you guys don't feel too bad about that. I tried to go slowly.